So far I've shown two different ways to solve this equation here. We find that this is the solution. The first way I showed was using a generating function, and the second way I showed was using induction. So I think that these two methods go really well hand in hand, and so that's what I'm going to talk about in this video. And then also I want to mention that over all of the rest of the videos that I'm going to record, I'm going to show a total of 6 different ways to solve this. So, using the generating function, first we define the generating function. We say that it's just a power series where each of the coefficients are equal to each term of the sequence, the f of n sequence. What we find is that this thing is equal to this rational function when it converges. In other words, this rational function, where it's analytic equal to its Taylor series, it's equal to this generating function. And so the idea is we're trying to solve for f of n, and so we can just manipulate this thing and see if it'll tell us the answer, and it does. I'll put a link here to the video where I show how to do that. And so the idea is you can just work with this thing strictly where it's analytic. You can just, you can talk about this rational function, but only be talking about the analytic part. And so I think that it works, it's a rigorous way of getting to your solution. But from a personal standpoint, I don't find it very satisfying because I don't really know whether this thing is convergent or not anywhere. Well, actually, okay, you know it's convergent at 0, and that would be true for all power series that are centered at 0. So you can see here, if you plug in x is equal to 0, these all cancel out, and you just get f of 0 is equal to big F0. So that's fine, but suppose this thing was only convergent when x is equal to 0. So that would mean if all these cancel out, then if you plug in 0 here, these cancel out, this cancels out, the a's cancel out. You might as well not lug around this rational function. You just have f of x is equal to f0. And what you see is that that this series is no longer, the generating function is no longer dependent on f of n. So how could it possibly tell you what the solution to your problem is in terms of f of n if it's not even dependent on f of n? So for me, I would like to know that this thing is convergent for some other value besides 0, because you plug in some other value besides 0, like here, you see that all these things will have a number in them, and so your series will take into account every single term of the sequence. So I would say, even though you can just work with this thing when it's analytic and just forget about when that actually happens, personally I find it to be assuming that to actually continue here, you're kind of assuming that it is analytic somewhere other than just 0. And so I think that you're assuming that it's analytic on a radius of convergence around 0. And why is this a symmetric radius of convergence around 0? I'll leave that as an exercise for you. This is true about any power series centered at 0. Whether or not these endpoints are included is a different story, but I'm just writing it like this. So one way you can determine the convergence of this series is by using the ratio test. And so to do that, you look at the n plus 1th term and you divide it by the nth term. And so this is what you get in. The ratio test says if that ratio, as n approaches infinity, is less than 1, that implies that the series converges. If it's greater than 1, that implies that it diverges. If it's equal to 1, then the ratio test is inconclusive. So if you take this and you jiggle it around a little bit, you'll see that this is equivalent to saying these x to the n's cancel out, and so you have x, absolute value of x, must be less than this. If this is true, then that implies that the series converges. So, looking at an example, if you look at the Fibonacci sequence, you can look at these different terms here. If you look at the nth term divided by the n plus 1th term, you see that as n approaches infinity, these very quickly approach this constant here, which happens to look a lot like the golden ratio conjugate, or actually the negative of the golden ratio conjugate, since the golden ratio conjugate's negative. And so that would imply that the radius of convergence is that x may go out as far as the golden ratio conjugate, because if x must be less than this for convergence, then that would mean this thing here is the radius of convergence. So in this case of the Fibonacci sequence, you see that the radius is about 0.62, the golden ratio conjugate. And so, like, the idea is that any equation that looks like this, you could just look at those terms and you'd see that's a pretty good indicator, a numerical indicator, that yes, this thing will converge. So you get to your solution, but I think that it's kind of under the assumption that the radius of convergence is greater than 0, because only in those cases when it converges outside of 0 are all of these other terms going to come into play, and could you possibly get an f of n solution that like makes sense? If it were only 0, then the next terms could be whatever they want. And of course that doesn't make sense, because you know that looking at this series, if you know any two consecutive terms, you know f3 and f4, you should be able to plug in n is equal to 3, rearrange this thing, and figure out what f5 is. So you get to your solution, and there's a cool corollary that you get if you go through this process, which is that you find the radius of convergence is the minimum of the reciprocals of the two lambda values that were in your solution. And these actually, the reciprocals of these lambda values end up being, those are just the roots to the denominator of this equation here. So, okay, so that's kind of cool. So then for the induction, it's pretty self-explanatory. You just do a proof by induction. You suppose this is your answer and you say that, oh yeah, that's correct. And I think that that's really useful, because even though the first method I mentioned, it could be rigorous as long as you're assuming that you're only working with that rational function where it's analytic. On a personal level, I find that kind of weird and hard to believe, just because you don't actually know whether or not it is convergent without using some numerical methods. So I like the proof by induction, because I think that it kind of like says, okay, well, is this the answer or not? And then it tells you, yes, it actually definitely is. And so you get another cool corollary from the proof by induction, which is how to solve for those lambda values. They're just the roots of this equation here called the characteristic equation. And so I want to show how you can actually apply these and solve one of these equations. So let's see, I'm going to do it in pen, hopefully I don't mess up. So, for example, Fibonacci sequence. This is the Fibonacci sequence. I'm gonna say f0 is equal to 0 and f1 is equal to 1. The reason I choose this and I don't say f1 and f2 are both equal to 1, these are equivalent, but it's just going to make it slightly easier in the end. So what you can do is just rearrange this. It's a lot like solving a differential equation. And then you look at the characteristic equation. A is 1, B is -1, C is -1. And what you find is that the values for lambda are just the golden ratio and golden ratio conjugate. And if you don't know what those are just the roots of this equation. So they're just a couple algebraic numbers. And so what you find is then, using that general solution that you find, is that Fn must be equal to constant times golden ratio to the n, and another constant times golden ratio conjugate to the n. And then all you have to do is solve the initial value problem. F0 is 0, F1 is 1, so you have 0 is equal to, this is just going to be C1 plus C2, 1 is equal to C1 golden ratio plus C2 golden ratio conjugate. You have this system of equations here. This tells you that what it's going to tell you is C1 is equal to the root 5 and C2 is equal to negative root 5. And so what you get in the end is your solution is, if you factor out that root 5, you get root 5, and then, oh, I think it's actually, is it 1 over root 5? I don't remember. I don't want to actually solve it. I think it is 1 over root 5. So you get this. This is just golden ratio to the n minus golden ratio conjugate to the n. And so you get the same solution. And you have this really fast, efficient way for getting it now.